Hello and welcome back to the deep dive. Today we're focusing on something that's probably in your kitchen right now, but it's structure. Well, it unlocks some of the most fundamental rules in organic chemistry.
It's good to be here. And yes, you're right. We're talking about a topic that, it really connects everyday things like the vinegar you use for cooking to the complex reactions you need to master for your exams.
We are doing a deep dive into Unit 8, Topic 6, Nomenclature and Structure of Carboxylic Acids. This is from the Aldehydes, Ketones, and Carboxylic Acids unit. Now, before we get into any definitions, I have a simple question for you listening at home.
A question based on what you see in the lab.
Exactly. Just think about vinegar. It looks just like water, doesn't it? A clear liquid. But what happens when you take a drop of it and put it on blue litmus paper?
The classic test. It turns red instantly.
It turns red, meaning it's an acid. But here's the confusing part. Alcohol, say ethanol, also looks like water. It also has an oxygen atom. But if you put ethanol on that same litmus paper, nothing happens. Why? Why does vinegar have this acidic power while alcohol is just neutral?
That is the perfect place to start. And the answer isn't some kind of magic. It's all in the structure, the very thing we're discussing today.
And why should our listeners really care about this, apart from, the sour taste?
Well, for your exams, this is critical. This structure explains why some organic compounds behave as acids and others don't. If you understand the structure now, you will be able to predict reactions for the rest of this unit. It's really the foundation.
Okay, so let's start right from the basics, the core idea. The name itself, carboxylic acid, sounds a bit technical.
It does, but the name is actually a very big hint. If you look at the word carboxyl, it's basically a hybrid, a mix of two things you have already studied.
A hybrid. Okay, let's break that down. A hybrid of what?
So think of the first part. Carb. That comes from carbonyl. You remember the carbonyl group, right?
Yeah.
The C double bonded to an O that we saw in aldehydes and ketones.
Right, CO, the carbonyl group. Got it.
And the second part, oxyl. That comes from the hydroxyl group, the AOH group from the alcohols chapter.
Wait, so you're saying it's just carbonyl plus hydroxyl together?
Precisely. That is the zero-level explanation. You take a carbonyl group and a hydroxyl group, and you put them on the very same carbon atom.
On the same one? That sounds a little crowded.
It's a very specific arrangement. I want everyone listening to just visualize this. If you can, close your eyes. Imagine a single carbon atom.
Okay, carbon atom is there.
Now, from that carbon, draw a double bond going upwards to an oxygen atom. That's your carbonyl part.
C double bond O, pointing up. Okay.
Now, from that same carbon, draw a single bond going to the side, connecting to an OH group, your hydroxyl part.
So on one single carbon, I have a CO and an AOH.
Exactly. And that combination has a special name. It's called the carboxyl group. We write it as COH.
It's like a double threat then. It has both parts.
And that combination is what changes everything. You see, the carbonyl oxygen, the one with the double bond, it's very electronegative. It's, greedy for electrons. It pulls all the electron density towards itself.
So what's actually happening at the particle level?
Because that double bonded oxygen is pulling electrons so strongly, it makes the OH bond right next to it very, very polar and weak. The hydrogen on that OH group is now held very loosely.
So because it's held so loosely, it can just fall off.
In chemistry, we say it can be donated very easily. It leaves as a proton, H plus Hanton. And what's the definition of an acid? A substance that donates a proton.
Ah, that makes complete sense. So the structure itself, having that greedy CO neighbor, makes the hydrogen want to leave.
That's it. And this leads us to the proper anchor definition for your exams. If you're asked, you should write. Carboxylic acids are organic compounds containing a carboxyl group, COH, bonded to a carbon chain, characterized by the presence of both a carbonyl CO and a hydroxyl OH.
I'll just repeat that for everyone taking notes. Carboxylic acids are organic compounds containing a carboxyl group, COOH, characterized by the presence of both a carbonyl and a hydroxyl group.
Perfect. Now, one very important point here. We have to clear up a common confusion, a sort of misunderstanding trigger.
What's that?
Many students, they see the AgOH in the formula and immediately think, oh, it's an alcohol. Or maybe that it's similar to a phenol.
I can see why they'd think that. They both have that OH group.
But you must not confuse them. The neighbor makes all the difference.
Yeah.
In alcohol, the carbon with the OH is just a normal carbon. But in a carboxylic acid, that carbon is also double bonded to another oxygen.
The CO neighbor changes its whole personality.
Completely. Just seeing an OH is not enough. The CO changes everything.
That's a really key distinction. So let's talk about the why. We
Right.
know the H plus is released, but things in chemistry don't just happen randomly. They happen because the result is more stable, right?
That's the golden rule. Stability. Everything moves towards a more stable state.
So you have a great analogy for this. The splitting couple. How does that work?
Right, so let's picture this. Imagine a couple trying to carry a really heavy sofa. This heavy sofa represents the negative charge.
Okay, so the negative charge is the heavyweight.
Now, when an acid gives away its proton, it's H plus 2. What's left behind is a negative ion. We call it the conjugate base. For carboxylic acids, this ion is the carboxylate ion.
The H plus is gone, and we have the carboxylate ion with a negative charge.
Yes. Now imagine if that negative charge, that heavy sofa, had to be carried by just one person. Just one oxygen atom all by itself.
That would be very unstable, very stressful for that one person.
Exactly. And that's what happens in an alcohol. If an alcohol loses its proton, the negative charge is stuck on one single oxygen. It's unstable.
Right.
So the alcohol says, no, thank you, I'm keeping my hydrogen. I don't want to carry this load alone. That's why they are not acidic.
Okay, so what's different in a carboxylic acid?
Here you have two oxygen atoms. And through a process called resonance, they share that heavy load. The negative charge isn't stuck on one oxygen. It's spread out. It's delocalized across both of them.
So it's like the couple is sharing the heavy sofa. They're carrying it together.
Precisely. Because they share the load, the whole ion is stable. It's relaxed. And because the resulting ion is so stable, the original acid is very happy to let the proton go in the first place.
That's a brilliant way to see it. The stable splitting couple makes the breakup losing the proton much easier.
You can also think of it like a perfectly balanced seesaw. The charge is balanced between the two oxygens. This idea is called resonance stabilization.
Resonance stabilization. That sounds like a keyword for the exam.
It's the most important phrase. In your board exams, if you get a question like, give reason. Why are carboxylic acids acidic? Ellis, your answer has to include this. Because the conjugate base, the carboxylate ion, is stabilized by resonance.
Stabilized by resonance. Everyone, please underline that in your notes.
And this concept, it explains why we even need this topic.
Mm-hmm.
Without understanding resonance, we could never explain our original question, why vinegar is acidic but vodka is not.
Right. In ethanol, there's no sharing, no resonance, so no stability.
Exactly. Structure dictates function.
Okay, I want to guide our listeners through a quick mental movie on nomenclature, the naming part. The IUPAC system is logical, but I know there's one common mistake students make.
Yes, one crucial rule that is so easy to forget.
And what's that rule?
You must always, always count the carbonyl carbon, the C, from the COH group as carbon number 1.
Always, no exceptions.
Always. It is the head of the chain.
Okay, let's try to name vinegar. The formula is HOSH.
Right. Picture that. She connected to COH. Now let's count the total number of carbons.
Okay, so there's the carbon in the CH group, that's 1, and the carbon in the COH group itself, that's 2. So 2 carbons.
2 carbons. What's the parent alkane name for 2 carbons?
That would be ethane.
Correct. And for carboxylic acids, the suffix we add to the end is oic acid. So you take ethane, drop the E, and add.
Ethanoic acid.
Perfect. Ethanoic acid. That is the IUPAC name for acetic acid or vinegar.
Okay, let's try another one. What about the simplest one? HCOH.
Good one. HECOOH. How many carbons do you see?
Just one. The one in the COH group itself.
Exactly. Parent alkane for 1 carbon is methane. So it becomes...
Ethanoic acid.
You've got it.
Yeah.
Methanoic acid. It's also known by its common name, formic acid.
Formic acid. Isn't that the stuff in red ant bites?
It is, yes. The stinging sensation you feel from a red ant bite is because it injects methanoic acid.
Ouch. Okay, so the rule is simple. Count the COE postcarbon as number 1 and add OAoic acid.
It is, as long as you remember to count that carbon. That's the most common mistake.
Let's connect this back to some real-world examples now. We already talked about the observable phenomenon of vinegar and litmus paper.
Yes, and if you take that a step further in the lab, if you add a base, like NaOH, the acidity disappears. You neutralize it, forming salt and water. A very common practical experiment.
What about technology? You know, I often see sodium benzoate listed as an ingredient on packets of chips or in juices.
That's a perfect technology application. Benzoic acid is a carboxylic acid where the COH group is attached directly to a benzene ring.
So it's an aromatic carboxylic acid.
It is. And it's used as a food preservative. That specific structure allows it to stop the growth of microbes, like bacteria and mold.
So the structure itself is what stops food from spoiling.
In a way, yes. It's a fantastic real-world application of the chemical properties we're talking about.
Okay, here's a counterintuitive example for you. We say carboxylic acids are weak acids, especially compared to mineral acids like HCl.
That's true. They don't dissociate completely in water.
But how do they compare to alcohols?
Now, this is where it gets really interesting. You might look at them both, see the OH group, and think, okay, they're probably similar in acidic strength.
That would be the natural assumption.
But actually, carboxylic acids are roughly 10,000 times more acidic than alcohols.
Wait, 10,000 times.
Yes, it's a huge, huge difference. And the reason is resonance. That splitting couple effect is incredibly powerful. The stability it provides makes an enormous difference.
Wow, that really drives home the point. A small change in structure, just adding that CO has massive consequences.
Absolutely. Structure determines property. That's the core of organic chemistry.
All right, as we get close to the end, let's make sure our listeners have everything they need for their exams. Let's run through the exam-safe clarity lines.
Good idea. Think of this as your final revision cheat sheet. I'll state the line, and you can tell us why it's important.
Ready?
Clarity line 1. The carboxyl group, COOH, is a combination of carbonyl, CO, and hydroxyl on the same carbon. It is not two separate groups.
This is important because that combined structure is the source of all its special properties, especially the acidity. You can't analyze them separately.
Correct. Clarity line 2. In IUPAC naming, always count the carbonyl carbon as carbon number 1. The name ends in oic acid.
This is a must-remember rule to avoid silly mistakes. If you miscount the carbons, your entire name will be wrong. HCOH is methanoic acid, not something else.
Clarity line 3. Carboxylic acids are acidic because their conjugate base, the carboxylate ion, is stabilized by resonance.
This is the money line. This is the standard, perfect answer for any give-reason question about their acidity in your board exams.
And the final one, clarity line 4. Alcohols are not acidic or are extremely weak because their conjugate base has no resonance stabilization.
This is about avoiding confusion. Don't mix them up. No CEO means no resonance, which means no real acidity.
Excellent. If you remember those 4 lines, you are in a very good position.
This has been super clear. Let's just do a very quick summary to tie it all together before we sign off.
Let's do it. First, the core idea. Carboxyl group is a hybrid of carbonyl plus hydroxyl, making COOH.
Second, the analogy. Remember the splitting couple or the seesaw? The negative charge is shared between 2 oxygens because of resonance, which means stability.
Third, the naming. Count the CO carbon as number 1 and add the suffix agoic acid.
Fourth, the key example. Vinegar or ethanoic acid turning litmus paper red is the classic proof of its acidic nature.
And fifth, your exam tip. The magic words are resonance stabilization. That's your key to explaining acidity.
And don't forget that massive difference in strength. They are 10,000 times more acidic than alcohols, all because of that stability.
That's the power structure.
I want to leave all of you with one final thought. Just think about the power we've been discussing. By simply adding a double-bonded oxygen next to an OH group, nature transforms a nearly neutral molecule like alcohol into a reactive acid that can preserve our food and drive biological systems.
It's the elegance of organic chemistry. Small changes, massive impact.
And remember, mastering this structure now makes the rest of the unit so much easier to understand. If you know why that proton leaves, you can predict what happens next in a reaction.
Exactly. So keep practicing those structures.
Thank you for listening to this deep dive. Good luck with your studies. Keep asking questions, and we'll see you for the next topic.
Goodbye and happy learning.